It's a pleasure to introduce our third and last speaker for today, Shu Sasaki from Queen Mary University in London. And his title, it's conveniently on the screen, a cell-weight conjecture for mod P Hilbert modular forms. Shu, please.
Thank you very much. Thank you very much for giving me the opportunity. So I want to talk about, Serre's conjecture and the geometry of Shimura varieties, in my case, geometry of Hilbert modular varieties. So which I suppose is perfectly in line with the theme of the workshop. So to start, so this will be everything I'm going to say is a joint work with Fred Diamond. And occasionally I will mention my work with Payman Caspe and Diamond. So these will be referred to DS or DKS. But basically I wanted to warn you that my notes here, the slides here, contain a lot more information than I intend to talk about. So my slides actually will be available on my website. If you look there, you can actually have an exact same copy of what I'm using here. So if you want to, go back a few pages yourself, you can find it there. So because it's about Serre's conjecture, I want to start by recalling, probably it's not necessary for this workshop, but let me just start with what Serre's conjecture was about, and then building up from that point onwards. So let P be a rational prime, and rho bar be a two-dimensional representation of the absolute Galois group of the rationals over FP bar, which I assume continuous, the odd, and the irreducible. Now, Serre's conjecture, so originally formulated in 1987 in his Duke paper, says that, one can basically define two invariants, K rho bar and N rho bar, associated to the mod P representation rho bar. The first one, K rho bar, is integer greater than or equal to 2. And the second one is, in fact, the anti-conductor prime to P and greater than or equal to 1. And in fact, there's a third invariant, the character, but I'm going to ignore that tacitly and just focus on these two for now. And the Serre's conjecture basically says that there should be a cuspital modular eigenform F of weight K rho bar and level N rho bar, such that its associated mod P representation, mod P Galois representation, which in the form of the reduction modulo P of sort of characteristic 0 Galois representation associated to F in the sense of Aikido Shimura, Delin, and so on, would recover the rho bar you start with. So generalizing the weight part of the Serre's conjecture, or loosely put, if rho bar is modular, what weight exactly would arise from rho bar has been, the question about the generalizing weight part of the Serre's conjecture to the setting of mod P Hilbert modular forms, in particular for regular weights, was initiated by Basil Diamond Jarvis in 2010. This topic has been developed further by Michael Schein, Heltzig, Florian Heltzig, David Savitz, and Toby G, and so on. But so this original BDJ conjecture itself, when P is odd, has been proved almost completely by G, Liu, and Savitz, and possibly some others. But the story of Serre's conjecture for Hilbert modular forms does not really end here. So what I want to talk about is emphasize that point. More precisely, today, what I want to do is to formulate a Serre's weight conjecture that includes, that reads all weights, not just the regular weights, but for all weights within the geometric theory of Hilbert modular forms that has sort of been initiated by the Katz in the 70s and the Goren, Andrea Goren, and so on. So it may be helpful just to give you a heads up. It's in a sense that we are trying to do what Edith Sorben did in 1992, reformulating Serre's original conjecture in a sort of geometric context and includes the weight ones, but somehow the generalizing sort of geometric theory, but generalizing the context from elliptic modular forms to Hilbert modular forms involves a little more intricate geometry, and that makes story harder to sort of keep track of. So that's what I want to talk about. So sort of in a nutshell, what I want to emphasize is that geometry with Shimura varieties seems to provide a genuinely new input into the mix, And to elaborate this point is somehow the goal of my talk. Okay, so to start with, I'm going to set up a few notations. So I'm going to fix algebraic closures, Q bar, QP bar, FP bar, and fix an embedding once for all, iota that goes from Q bar to QP bar. For me, sigma always is going to be the set of embeddings from F into QP bar, so the periodic embeddings. And I am going to assume that there's only one prime V in OF above P. So it can be, the unramified or ramified, and FV, the capital F, is going to be the residue field at V. Okay. So if I denote FVR to mean the maximal unramified extension of QP of degree residue class degree FV, so this is inside FV, then the restriction to FVR, so there's R missing here, defines a surjection from the set of all the embeddings of F into the QP bar to the set of all the embeddings of FV of them, of FVR into QP bar. And this surjection is EV to 1, where EV is a ramification index of V, in the sense that if I take the element vita on the right, on the right, that doesn't look good at all, okay. So vita on the right, then its preimage consists of EV embeddings. So in a sense, they are basically the roots, EV roots of the Eisenstein polynomial, whose coefficients are given by the image of the coefficients of the Eisenstein polynomial over FVR by the beta. And so in a sense, I've got two parameters in some sense. So the vita would read the unramified part of embedding of F into QP bar, and the index sitting on to the right, so the i's I would typically say. So the i's would read the sort of ramified part, sort of specifying how a fixed uniformizer would act. It would tell you how the fixed uniformizers would be sent to. So on this set of embedding F into QP bar, I'm going to define the shift operator. So this, I'm going to call it phi. I think Payman called it sigma. So these EV of them are sort of indexed by, so unramified part of the embeddings is all vita. Within those vita ones, they are the preimage of the vita. My big phi would shift sort of i's from I plus y to I plus 1 and so on. And once you get to the EV, you get to the next sort of packet where the unramified part is given by the phi twist of vita. So the phi is the Frobenius, absolute Frobenius, shifting sort of by 1. And it goes around all the way to, then you would come back to here. When I said phi to the minus 1, this is, you could think of it as a phi to the FV minus 1, shift over vita, and so on. So it goes around it all the way. So the shifter, this shift phi will do just one next to each other, except that when you get to EV, you get something else. Okay, for me, the G is going to be the rest of GL2, and I'm gonna use gamma to denote the open compact subgroup of the adelic point, a finite part of adelic point of G. And I'm going to assume that it's maximal compact and hyperspecial at P. So this is the analog of P doesn't divide level N. And that I'm going to assume that my level open compact subgroup is sufficiently small in some sense. I'm not going to define what I mean precisely. So attached to gamma, so analog of level prime to P, there is a smooth integral model Y gamma over ZP bar, whose Z points will recover the double coset for G. And let me just elaborate how you get it. So it's not exactly true that Y gamma is given by the moduli problem. In fact, the corresponding group will be the smaller than the G, the rest of GL2, but I'm going to ignore the difference, and I'm just going to say, well, Y gamma would parameterize the following data, which is that Hilbert Broomington Abelian varieties of PL type So I'm not going to specify what these things mean, but in payments talk, these things were somewhat carefully defined. So A goes to S with structural morphism S, such that if I consider the push forward along the structural morphism of the relative sheaf of differentials, if I denote it omega, this would break up according to how unramified part of FV acts. So this would be a direct sum. So the FB, I've got a FB pieces, each of which each omega beta is locally free of rank EV over OS. And as Payman mentioned, this modular, well, this integral model would parameterizes those where omega beta or rank EV comes equipped with a filtration or complete flag, which I do not like this, where so the I index, the one would indicate the rank is 1, EB would indicate the rank is EV. So this is the top piece. And the condition, the key piece of information is that OF acts via tau on this graded piece, tau, when tau is of the form beta now, I. So as I mentioned, the beta would read the unramified part, the I would read the ramified part, or how uniformizer would act. And so for every choice of beta and I can specifically see in which graded piece, and that's how our OF should act. And the number numerology would work out. So this breaks up into the FB pieces, each of which has got EB pieces, and so on. Right. So now I'm going to define automorphic bundle as follows. So given a pair of d tuples of integers, so d being the degree of f over q, a pair of d tuples of integers, k and l, I can define the automorphic bundle as follows. So the AKL is going to be the tensor product over all tau that ranges over the sigma, the set of embeddings from f into qp bar. So I'm going to tensor up all the invertible sheaves here, where the omega tau is a graded piece of rank 1, and I'm going to raise it to the power k tau, and delta tau is defined similarly, but instead of starting with little omega, so the push forward of relative differentials, I'm going to consider the relative Durham cohomology sheaf, which is OF tensor or S or Y gamma of rank 2. So if I take the wedge, I get OF tensor or Y gamma rank 1. And this would give me the sort of same decomposition plus the same sort of filtration, in this case canonical, on that. And you would do the same operation, raising to the power L tau, prescribed by the numbers I'm given there. So for me, the space of multi-Hilbert modular forms, so weight KL and level gamma, so the gamma I would emphasize again is an analog of level prime to P, is defined to be the space of the global sections of my automorphic bundle AKL over the special fiber Y gamma. So I define the Y gamma to be defined over ZP bar, so I'm going to take just the fiber P. So this would be the special fiber, and I take the global section of it. The element is my multi-Hilbert modular form. So what is the fuss? Well, when F is not Q, then it is known that, well, it's a standard fact that every Hilbert modular form of weight KL over QP bar or characteristic 0, Hilbert modular form would have to have a weight Paritius, in the sense that the K tau plus 2L tau is independent of tau. So that means that there are lots of Hilbert modular forms, so these are the ones on the right, which are not in the image of it, because those in the image are necessarily of Paritius weight. So if I consider the Hilbert modular forms here of KL non-Paritius, then they are not coming from characteristic 0 of level gamma. So I should probably emphasize that they're not coming from the same level, gamma and gamma. So that makes this theory a little more mysterious. In the classical case, what happens is that, well, this would be almost always surjective when the weight k is greater than or equal to 2, or level is greater than or equal to 2. But so most of the time, this will be the surjective, but in Hilbert case, suddenly it is no longer the case, and there are tons of those things that are not in the image. That makes MOP theory of Hilbert modular forms, geometric theory of Hilbert modular form, a little more complicated than the classical case. What makes the theory a little more, even more complicated, is that in stark contrast to the F equals classical case, there are lots of MOP Hilbert modular forms of partially negative weights. So in the classical case, when F equals Q, there aren't modular form, MOP modular form, even character 0, MOP modular forms of negative weights or negative weight. But in Hilbert case, there are, and I'm going to give you an example in the form of a partial Hasse invariant. So in the classical case, the partial Hasse invariant has got a weight p minus 1, and in the Hilbert case, somehow those numbers p and minus 1, etc., would all sort of breaks up into the pieces. So I'm going to sort of quickly recall the definition as, well, this was explained by Payman, but there's no harm in repeating it here. So the relative Bersheibon, or the dual of relative Frobenius on the dual Arvinian variety, Hilbert-Blumenthal Arvinian variety, would give you the map from A to the P to the A. And this would give rise to the pullback by Bersheibon, which if you restrict to the beta piece, so unramified piece, the beta is the unramified part of the embedding, then it will give me the map from omega bar to the beta to the omega bar p to the p of sigma or the phi inverse of beta. And this map then breaks up into small pieces on the graded piece, which I denoted like that. So that goes from this to this. So this will be the sort of given by the Shibon at this level, and this sequence of morphisms, each of them would give rise to sort of, if I've got a map from here to here, you can think of it as a global section over the line bundle given by the joule of this times the target. So that translates into the weight indexed by, for example, in this case, this embedding and this embedding. And that will give you sort of -1 in particular for the source. And the target would give me the positive weight. And so in particular, so this would correspond to this. And these are all other cases. Okay. So the first theorem I want to advertise is the following. So let F be a mod P Hilbert modular form of weight KL, no condition on KL, not pernicious or not, of level gamma. As always, gamma is a sort of analog level prime to P, sufficiently small, and let S be a finite set of finite places in F containing all the places V above P and all the places V that appear in the level. So in the sort of in the group theoretic language, it means that the maximum open compact subgroup F GL2 or OFB is not contained in gamma. Now I furthermore assume that my mod P modular form F is an eigenform with respect to the TB is the sort of 1, 0, 0 uniformizer V, and SV is the diagonal one with eigenvalues alpha V and beta V respectively for all V not in S. And then the upshot is that there should be a mod P continuous Galois representation associated to F, which is unramified outside S, and its characteristic polynomial at V not in S of the image of Frobenius at V is what you think it should be, that degree 2 polynomial of this form, that x squared minus alpha bx plus the beta V plus norm of V. Okay, so I should make a remark. So the novelty of this theorem is that, well, this pair of d tuples of integers k and l does not have to satisfy the Parisian condition. In fact, when it satisfies the Parisian condition, the construction of modular Galois, mod P Galois representation has been known by Emerson, Reducci, Chow in a ramified case, Reducci, Chow in the ramified case, and the Golgi and Koski-Velter in general Shimura varieties, well, like more than well, more general than the Hilbert modular variety, but so the non-Parisiousness is something that has been missing. So that would so the construction of mod P Galois representation, modular Galois representation, would make the folklore conjecture a little more tangible, which says that if I'm given a two-dimensional Galois representation over FP bar, totally odd, continuous and irreducible, then such a Galois representation should arise from mod P Hilbert modular form in the sense that I defined. So let me just give you an idea of the proof. I have in my slides, I've written proof, but absolutely not possible to talk about it within 50 minutes. So I'm not going to talk about it, but I left everything in the slides. So if you are interested, you can have a look. So I'm gonna sort of give you an idea of how to prove that theorem when the ramification index is 1 in a ramified case. So as I mentioned, the issue about reduction modulo P at the level of Hilbert modular forms, the geometric Hilbert modular form, is that it is not surjective. The reduction modulo P is not surjective. We can translate it into the fact that, in fact, not every Galois representation rho bar arises as the reduction of character to 0 eigenform of level prime to P. So it doesn't seem like a very good idea to sort of keep wondering how to lift my mod P modular form that I'm given to character 0 modular eigenform of the same level or level prime to P. So what we do instead is to, well, try to lift mod P Hilbert modular form of parallel weight, but level being the gamma and the gamma 1P. So what you do is, starting with my modular form F, you're gonna hit this by a bunch of Hasse invariants. You increase the weight, you get to the sort of parallel weight, and then you try to observe that such a thing would actually lift to character 0 if the level is gamma 1P. So that's the sort of idea, and the more precisely, this parallel weight would come with sort of two pieces of information that I'm going to sort of want to get the weight to be n+2, where n comes from sort of a parameter you need to make appeal to the results that there is an ample line bundle defined over the level prime to P compactified Hilbert modular variety. So I can sort of arbitrarily raise this n big and big, so that sort of H1 coherent cohomology would vanish if the level is gamma 1P. And the two would in fact come from a dualizing sheaf, but I think I shouldn't go even further than that. So I've just given all these there, but I'm going to skip those. And in the ramified case would follow similarly, except that it needs a little bit more work. Okay, so so far what we've done is that, well, if I'm given a mod P Hilbert modular form, geometrically defined, level prime to P, of whether it's a Parisian or not, there is a mod P Galois representation. So what I want to do is now to formulate a conjecture about exactly what kind of weights would show up if I'm given one mod P Galois representation rho bar. So in preparation for that, I'm going to give you the following definition, which has been introduced by Payman's talk. Let me just recall quickly what they are. So for me, so the CDK, so this was defined, I think this was called C min in Payman's talk. So this would be just set of tuples K, the weights of this form, where P times K tau is greater than or equal to this when tau is of the form tau beta 1 and at other places there. So probably let me just finish the definition and then I'm going to draw a picture. The C now is going to be the subset of all weights K living in this minimal cone in payment sense, such that it's greater than or equal to 1 for every single index. So as I promised, I'm going to give you a picture. So when EB is 1 and FV is 2, the picture, so I'm going to have, this is a beta, and this will be the phi beta or phi inverse of beta. So this is 1 and P, and I'm going to have a line goes here, line goes there. So the CDK or CMIN in payments talk is this area region sandwiched by these two lines, and my C is the one in living in here. Okay, and you can draw a similar picture in the ramified case. It will be something similar, except that instead of 1P, I'm going to have a 1, 1. So the line would go through there. And then the something in between the two lines would be the C that I defined here in the quadratic totally ramified case. So the second definition I want to give you is this curly inequality, really bad notation, but so I'm going to go with that. So I'm going to call K is curly greater than or equal to K prime. So these are the tuples. If K minus K prime is a non-negative integer linear combination of the weights of partial Hasse invariants. Okay, so so that means that, so if I want to draw a picture. So again, my FB equals 2, EB equals 1 case. If my K prime is here, so this will be the 1 and P, is this really bad? Okay, oh, and this will be the P and 1. So my K, if K prime is here, the K would live any of the region here, which is sort of wider region than the this C that I defined, and I'm gonna come to that issue in a minute. So here's the conjecture that I'm formulating now. So let me just check the time. Okay, so the row bar is the what I'm interested in. So the two-dimensional representation of absolute variable group of F defined over FB bar. I assume totally odd, continuous, and irreducible. So I'm going to fix L in Z sigma, so one tuple. Then the conjecture says, well, then there exists K, a tuple, a D tuple of integers, sitting in the cone C, satisfying the following two conditions, or these two conditions that characterizes, in fact, this tuple, which is that rho bar is modular of weight KL, if and only if K is curly greater than or equal to K rho bar L. So morally, what this says is that, well, so amongst all these weights that makes a rho bar modular, there is a minimal one. By saying a minimum with respect to this curly inequality. So difference between those two numbers would be just a non-negative linear combination of weights of partial Hasse invariants. So that's the first input. So sort of a minimality of weight, that there exists something minimal amongst those modular weights. And the second condition is that if my weight K is in C, then the K is curly greater than or equal to the K rho bar L, is equivalent to saying that in fact it's a Galois representation restricted at this unique prime above P has a crystalline lift of weight KL. So one warning that I'm offsetting everything in terms of automorphic weights. So in other words, when I said of weight, what I really mean is of Hochstate weight. So this presence of Hochstate would make a difference. The Hochstate weight at K plus L minus 1, comma L. I'm going to go with this KL, the automorphic weight in what follows. So what this says is as long as my weight K is in my cone, then so basically all the modular weights will be characterized by the existence of crystalline lift of that weight, more or less. Okay, so I'm going to give you 2 examples actually, but before going to talk about that, I'm going to give you a few remarks and I'll get to the example. Probably the example will give you a better idea of what I'm talking about, but let me just first make a few remarks. So the first, so maybe I should just say here. So if I happen to know that a rho bar is a modular a priori, then the sort of our conjecture is in some sense sort of motivated by the fact that you can compute the weight iteration of a modular form F such that the rho bar is isomorphic to rho bar F. But unfortunately, that weight iteration at the moment lives only in the C min cone, in my case, the C of dk. So this allay thing. I would strongly suspect that this weight iteration would live in the C, the smaller one, but I guess I'm not qualified to talk about that for now. Another remark I want to make is the following. So assuming the existence of K rho bar L, which satisfy the first condition. So to recall, the first condition is about minimality, that there exists a sort of minimal possible modular weight given the rho bar. If I can assume that first condition, then the, well, because K rho bar L itself is clearly greater than or equal to the K rho bar L, it means that it is a modular. And so it implies in particular the folklore conjecture. And the more content, the more interesting fact is that, well, if the first condition is satisfied, then the second condition boils down to the checking the following, well, sort of conjecture, the conjecture star, which says the following, and this is example, this will be the case that I'm giving example in a minute. So the rho bar is my Mopi Galois representation, which I assume is irreducible and modular. If my K is in C, then the rho bar is modular over KL is equivalent to saying that in fact the restricted at decomposition group and V, it has got a crystalline lift of weight KL. Okay, so but it's simply that you could eliminate the sort of once the existence of a sort of minimum weight K rho bar L is assumed, then you can knock out the K rho bar L out of the equation and you can reformulate it, and this will be the format you will get, and nothing deep happening from translating that statement. On the other hand, if I've got a K rho bar L in C satisfying the second condition, not the first condition, then the main conjecture follows from just the conjecture star I've just mentioned in one slide above. If we happen to know the following fact, that if rho bar is irreducible and it's modular, then the weight iteration of that modular form that makes rho bar modular sitting inside C. If this conjecture is true, then the conjecture star would imply the main conjecture, or for in this case, the first condition about the minimality, because more or less this weight iteration would define the K rho bar L that I'm after. Okay. So as you can see that it's about the crystalline lift, and in fact the second condition is suggested strongly by the Breuer conjecture and the modular representation theory of GL2FB. And this is somehow the underlying theme of I work with Diamond and Casaway, and I probably going to mention briefly what this is about later on, but the inspiration was that. Now, one more remark I should make is that in the second statement, second condition, sorry, there says that as long as K lies in C, then the existence of a crystalline lift and K is curly greater than or equal to K rho by L is equivalent. But if K does not in C, then the implication that the K is curly greater than or equal to the K rho by L does not imply the rho bar has got a crystalline lift over KL. In fact, this is a sort of, you can actually come up with a counterexample. In fact, the counterexample is a local nature. So you can build a counterexample using periodic quantity theory. Okay, so let me give you an example finally. So here's a statement that you get if I specialize everything to F equals Q and L equals 0. The L weight doesn't really make much difference, in fact, because it's all about the twist of weight. So, I mean, L can be there, but I'm just gonna ignore that. That's what I mean by L equals 0. So when F is Q, then my minimal con, the C dk, is simply just a set of non-negative integers. And therefore, my C will be the set of all positive integers. And my curly inequality would simply mean that the difference between them is the non-negative integer multiple of the weight of a Hasse invariant, which is p minus 1. And if this is the case, then the statement said that there exists a K rho bar. So there used to be L here, but now I knock it down. So the K rho bar, which lives in C, which is to mean that greater than or equal to 1, such that the following three statements are equivalent. So the first condition amounts to the equivalence of these two, and the second condition amounts to the equivalence of these two. And that it says what the rho bar is modular of that weight, if and only if that weight would have to be what differs from the K rho bar by the non-negative integer multiple of p minus 1, which is then equivalent to the rho bar restricted at the decomposition group of P as with a crystalline lift of weight K0 or Hodge-Tail weight K minus 1, 0. So looking at this statement, what it seems to be saying is that the K rho bar there is the smallest possible weight for which rho bar is modular. And in fact, in Edith Solben's work in 1992, he proved that if rho bar is a modular, the predicted weight K rho bar, in his sense, is in fact a minimum possible by showing that actually that his K rho bar is exactly the weight for iteration of the modular form, corresponding modular form. So here we don't have to have that modularity assumption, but it sort of conjecturally said there should be a minimal weight. Okay. So that was the first example. Before giving you the second example, I've got 10 minutes. Okay, I want to give you. I want to talk about the work. How is our conjecture related to the Basel-Diamond-Jarvis conjecture? Well, it's a fair question. Let me give you the following definition. So, given a finite dimensional representation of a GL2 FB over FB bar. The BDJ defined following notion of algebraic modularity of representation weight V, which is that I'm not going to read out this. In a nutshell, it means that there exists a quaternion algebra split at all places above P, ramified at exactly one infinite place and ramified elsewhere. Ramified everywhere except at one place where it is split. And this rho bar, in fact, shows up in the first état cohomology of the Shimura curve corresponding to that quaternion algebra with coefficients in mod P état sheaf corresponding to the representation V. So, basically the rho bar would appear in the état cohomology of Shimura curve. up to some twist with the coefficient given by the representation V. So here's a conjecture that relates the notion of algebraic modularity to the geometric modularity that I defined. So let KL be a pair of decomposable integers, and I assume that to be regular in the sense that every single k tau is greater than or equal to 2. Okay, then so if rho bar is algebraic modular of weight KL, then rho bar is modular of weight KL. So what do I mean by algebraic modular of weight KL? Well, it is modular of representation weight VK 1 minus K minus L, so which is just about what you think it is. In fact, the symmetric representation to the power of K tau minus 2, and determinant we normalize this way, of the standard representation tensored over to the FB bar with the tau. I mean, strictly speaking, tau shouldn't be there. Well, in fact, what I mean here is the reduction modulo P of the restriction to the unramified part of the embedding tau, which is F goes to QP bar. So you can do it for every single tau, not just about unramified ones. Okay. Furthermore, so the first statement was saying that if rho bar is algebraic modular of weight KL, then it is geometric modular. You could go converse as long as K is inside Xi con. Okay, but this is not going to be true if the weight you start with is not in my con. In fact, we do know sort of many cases of that conjecture. We might call it a minor case. So it is in the following case: if rho bar is happen to be algebraic modular of Paritius weight, so the K tau plus 2 times L tau is independent of tau, then rho bar is a geometric modular of weight KL. So this is because if the weight is Paritius, then there exists the characteristic 0 Hilbert modular forms for the quaternion algebra, whose associated mod P Galois representation recovers rho bar. But if I'm given a characteristic 0 automorphic representation of more Hilbert modular form, then I can use Jacquet-Langlands to pass from that to the Hilbert modular form for GL2, and then consider its associated Galois representation and reduce modulo P. So that gives me that. But as I mentioned, you cannot go converse even if it's a Paritius. So the converse cannot be possible even if it's not, even if it's a Paritius. But you can still go converse from going geometric weight to the algebraic weight if you relax somehow about exact weight you want to hit. So by our construction of modular Galois representation, you would know that if rho bar is geometric modular of some weight, you do know that the rho bar is algebraic modular of some weight. Okay, so let me give it a recap before the sort of the most interesting part. So the conjecture was saying that, well, if I'm given the mod P Galois representation, there exists a K rho bar L, which is somehow characterized by the two conditions, the modular weight KL, if and only if K is curly greater than or equal to rho bar L. And these weights are characterized by the existence of Christian lift of that weight. And if you assume that there is a K rho bar L satisfying the first condition, the second condition boils down to the following statement, that rho bar is irreducible in modular, then if K is in Xi, then rho bar is modular of weight K, is equivalent to saying that the rho bar has got a Christian lift of weight KL. So here's the, well, the example I'm going to talk about is the unramified quadratic inert case. So I'm going to set the degree to be 2. My ramification index is 0, in which case my sigma is nothing other than sigma r. So all the unramified embeddings, all of them. I'm going to fix tau in in sigma. Then I can describe all 2 embeddings in sigma by tau and phi twist over tau, or phi inverse twist over tau. In the quadratic case, it doesn't make a difference. In quadratic inert case, it doesn't make a difference. So I'm going to always write number on the left if it's indexed by tau, and the number on the right is the number indexed by phi twist of tau. And I'm going to assume L to be 0. Then the statement is the following. Okay, so let R be an integer between 2 and P, strictly greater than 2 and less than or equal to P. My rho bar is irreducible and modular. Then the following is true. The rho bar, when restricted to a decomposition group at V, has sort of crystalline left of weight. So this would be the sort of K weight, if you like, and L weight is this. So the K weight index, so R is the what's indexed by tau, and this is the phi twist of tau. So if the crystalline lift of this, then the rho bar should be geometric modular of weight that. So you should note that if I translate into Hodge-Taylor weight, it would be just R minus 1 and 0. So one of these factors 0. It is sort of known, well, okay, so in fact, it is expected that if rho bar is unramified at V, in other words, Hodge-Taylor weights are all equal, or if my L is 0, they're all zeros, then rho bar is expected to arise from parallel weight 1 modulo P. And the partial cases are known by G and Payman. But the case I'm having here is something in the middle. It's not sort of all Hodge-Taylor weights 0 or equal, nor the Hodge-Taylor weights are distinct. So it's not the regular case that sort of here, the geometric Hilbert modular form that I should be getting has sort of partially weight 1. So somehow our conjecture manages to describe something that's not sort of Hodge-Taylor weights all 0, nor all greater than or equal to 1. And so that's the sort of statement I want to prove. The conjecture says that you can actually go to the converse, but I cannot prove the converse, and I'll explain why in, 3 minutes. Okay, so for brevity, I'm going to assume that the rho bar is of Taylor-Wiles type, it's absolutely irreducible when restricted to the f zeta v and the condition about p equals 5. I'll explain it will come clear why I have to assume that. So the assumption was that rho bar has got a crystalline lift of this weight. I'll just copy down from the statement. Then we deduce from p-adic Hodge theory that my local graph representation will actually have a crystalline lift of 2 different weights written. So this is just the sort of, ultimately p-adic Hodge theory, linear algebra, you could sort of come up with those lifts. It's a local statement. But second step is that, in fact, the work of G and his collaborators, Savit and Liu, on the BDJ conjecture actually says that piece of local information, local piece of information would actually translate into a global information, that a rho bar would in fact arise from algebraic modular forms of weight KL and K prime L prime, the pairs of integers I mentioned in one slide before. So by algebraic modular, this is just about the modular form for the quaternion algebra. Now the next step is to translate that into the geometric Hilbert modular forms. But you can do that because the R is R and I are 1 Parisius. So as I mentioned about the algebraic modularity equal geometric modularity conjecture, you can go from algebraic modular to geometric modular as long as the weight you start with is Parisius. So in this situation that I specified, in fact, I can go from algebraic modular of these weights to geometric modular of weight KL. So I'm now in the realm of the GL2. So let F and F prime respectively be the geometric Hilbert modular form of weight KL and K prime L prime. What you do, on one hand, you're gonna use theta operator at tau. This would increase the weight of F by this much. So this is my weight KL. And if you can do the addition, what you get is this. On the other hand, given the second geometric Hilbert modular forms I've got, I'm going to multiply that by the Hasse invariant at tau. So the multiplication would give me this increment in weight, and the sum of that would give me that. So magically these two, well, it turns out, not magically, these two sets of numbers would match up. And so the expectation is that these two forms should be equal, and you can indeed check that by sort of replacing, if necessary, by forms of higher level to make the coefficient, Q expansion coefficients 0 at the bar prime. So that those are primes which are not co-prime to the level. You can sort of match up every single Q expansion coefficient in both. So what does it say? Well, the punchline is the following. Now we can use the theorem originally proved by Andrea Goren, which says the following. So if I'm given I'm going to finish in a minute. So the Hilbert modular form of AKL, you can tell you exactly when the Hasse invariant at tau divides the image of f by theta at tau. And that's when either f is divisible by h tau or p divides k tau. So going back there, so the h tau divides theta tau f because of this inequality. So that leaves me that either p divides my weight of f, or the Hasse invariant h tau divides f. And as it turns out, the weight of f is r minus 1, k tau is r minus 1, which is not divisible by p. That means that f needs to be divisible by Hasse invariant at tau. So now I can divide by that theorem that, that what you get is the Hilbert modular form f modular f tau, whose weight, if you calculate this subtraction, this is the weight of Hasse invariant at tau, what you get is this number, which is exactly the weight that you want. Hence, this step is complete. So yeah, I guess I should. So I'll just one final remark. I'm overrunning. Okay, so 2 minutes. So the one remark is that, well, the argument is reversible, except that in that proof we could go from algebraic modular to geometric modular, modulo p, by the way, the algebraic modular to geometric modular, by making appeal to the Parisiousness of the weight. But even if it's a Parisius, you cannot go back from geometric to the algebraic, and therefore you cannot really reverse this argument. Apart from that point, you can. You can also prove the ramified case, and the numerology would look like that, but I think I've just overrun, so I'm gonna stop it here.
Okay, thank you, Shu, for a very beautiful talk.
Sorry.
We are inviting questions. If you do have a question, raise your hand. If someone you think I don't see that, just text me so I can give you permission a different way. And co-organizers, of course, we established that you can just go ahead and ask questions because you cannot apparently raise your hand. So if there are, yeah. Okay, so
I think maybe you lost the condition that R is odd in the statement.
Yes, thank you. Sorry, yes, R is odd, yes. Yes, that gives me the Parisiousness of R in 1. Sorry, I was really panicking for the lack of time, sorry.
So other questions or, oh, Matthew Emerton, let me just find you.
So how can I, maybe I should unshare.
Matthew. How are you?
Can you hear me?
Oh, yes, we can hear you, yes.
Okay.
Oh, yes.
Wondering, suppose I worked on some kind of unitary Shimura variety or something instead. So the Parisius aspect went away.
Right.
but the like the small weight aspects still survive.
Can I formulate conjectures for
Yeah, I
unitary
mean,
MOP?
I guess I kind of want to propose that there's sort of two issues. There's kind of the parity issue,
Right.
and then there's sort of the small weight issue, and then maybe I would have guessed they might be separate, but maybe they're not so separate. But I'm just kind of curious. I mean, how you think about those two issues, or how connected they are in the way you think about things.
It seems possible to formulate a conjecture, but it seems possible to.
I guess I would think of them as separate issues.
Okay.
Yeah, I would agree. I'm tempted to agree. Yes.
I mean, that kind of makes sense.
Right.
But you haven't sort of
thought
much about. You haven't really thought about.
No, absolutely not. Yeah, absolutely not. Yes.
Okay. Well, I mean,
how much about? So well, so there'll be a unitary. Yeah, but to start with, can you actually construct sort of a geometric multi-Hilbert modular forms or sort of full weights? Is it possible? I wonder.
I would guess that the Monp geometry looks fairly similar, and that
right.
I would guess that it looks fairly similar, but somehow maybe easier in some sense because you don't have to worry about parity conditions.
Yeah.
Well, yeah, I guess I don't have a good feeling right now for kind of what, how the parity conditions appear when you start making sort of geometric arguments. But anyway, but it's good to know that anyway that it's sort of should.
Well, the formulating conjecture could be possible, but then I don't know if you want to actually prove conjectures, as I kind of vaguely mentioned that you use these Q expansions. And I don't know how this will come into the sort of unitary setting when.
So if you were if you had a if you shifted from the Hilbert setting to some like some say quaternion algebra that has a ramification at infinity,
right?
You would have this. You also would be not able to work in that setting either, in the sense that. Like if you kind of took a
yes.
of your field, you would have the same issue that you don't have Q expansions.
Yeah, but if you want to prove the conjecture, yes, yes.
Wait, so sorry to prolong it, but can you just remind me, maybe in one sentence, where the Q expansion argument came in?
So I was saying in the proof of if rho bar has got a crystalline lift of some weight, then you should imply the geometric weight, the rho bar is modular of specific geometric weight. The way to prove that was that, well, starting with the crystalline lift of some weight, you produce two crystalline lifts of two different crystalline lifts of two different weights, and you translated that to the geometric Hilbert modular form, to a pair of geometric Hilbert modular forms of these weights. And you somehow match them up by, on one hand, you consider the theta operator, and on the other hand, you multiply that by Hasse. And the coincidence of these two forms would have to be proved. Well, we sort of proved that coincidence by actually checking the expansion coefficients.
So it's one of these kind of gluing arguments.
In a sense, yes. Yes, in a sense, yes. Yeah. So yes, certainly I wouldn't be able to.
That's very helpful. Thank you.
Thank you.
Okay, wonderful. Other further questions or comments about the talk? Okay, as far as I can see, and I have to say there are some glitches with Zoom, but as far as I can see, there are no more talks. It's been a wonderful and somewhat long day. So I think we're gonna end the recording now and maybe end our session for today now.